Hello folks, welcome to the latest edition of the Physics Corner with Dr. Christopher Sorolla. Today's episode we're taking a look at timing circuits, specifically RL circuits. So in the previous video we looked at RC circuits, or resistors, capacitors. Now we're taking a look at resistors and inductors. And remember, despite the fact that the word inductor starts with the letter I and there's no L in the word inductor, symbol is an L, so just something to know. Anyway, so RL circuits also can be used as timing circuits. Let's show you how this works. So let's suppose we have a battery of 1.5 volts. We connect that with a series, in series with a resistor of 20 ohms and an inductor of 4 millihenries. Let's find the maximum voltage across the inductor, the maximum voltage across the resistor, the maximum current through the circuit. That's a hint as to how I'm saying that, as to what's going to happen. The time constant of the circuit, and the behaviors of the voltages and the current through the circuit, one time constant after we throw the switch. Now, the reason it's sort of talked about this way is because in an inductor circuit, we're not storing anything, or at least we're not storing stationary things. So in a capacitor circuit, the whole point is that you have charges accumulating on opposite sides of a capacitor, right? But that's not the case here. So we're not really storing charge. Now, if you want to say you're quote-unquote storing current, if you mean that there's going to be a set amount of current ultimately traveling through the coil of the inductor, I suppose you can go ahead and say it that way. But it's not really storing in the sense that you have something stationary. So while there will be some similarities between this RL circuit and an RC circuit, there'll also be some important differences. Something else to bear in mind as I'm going through this particular episode, since we already did a good discussion of the meaning of a time constant and what that talks about, how that's employed in the RC circuit video, I'm not going to spend as much time on that topic here today. So if you want to get more insight as to what the time constant is really all about, I refer you back to the RC circuit video. Okay, so here's our picture. Now, similar to what we did with the RC circuit, I'm going to write down our knowns as we usually do and our unknowns, and have a circuit diagram. So here is our source of voltage, a battery, delta V. Here's a switch. Here is our inductor, L, and here is our resistor, R. Just like we've done for a lot, not every, but a lot of the circuit symbols are drawn in such a way as to remind you or resemble what the device actually is. So like a resistor is kind of like a speed bump sort of look to it, and a capacitor symbol, at least for physicists, is looking like a parallel plate capacitor. The circuit symbol for an inductor looks like a miniature coil of wire, because that's what an inductor really is, right? It's a coil of wire. So that's what to look at. Now, because this isn't storing any charge, charges are going to be moving once we close the switch. There's no charge, for example, stored on anything at the moment in any real sense. We'll have current flowing through it. Now, again, I'm going to let your lecture instructors talk about why this works this way, but because of the way that coils work and because of how Faraday's law works, specifically the negative sign in Faraday's law, the coil, or the current through the coil, will actually not start at a maximum. It'll start at 0 and build up to a maximum. Okay, so that will have some interesting consequences as to what happens. So let's go through everything. All right. Sometimes we won't need to make a calculation. Of course, other times we will. So we throw the switch and then we wait and we ask, what's the maximum voltage across the inductor? What's the maximum voltage across the resistor? So on and so forth. So the moment we throw the switch, there is no current flowing through the circuit at this stage, which means since there's no current flowing through a resistor, there's no voltage across the resistor. So at time equals 0, no voltage across the resistor. Now that's different than the capacitor circuit. Remember, in a capacitor circuit, the current was a maximum at the beginning, not a minimum. Here, it's at a minimum. The current is going to take time to build up, it turns out. But if that means if there's no voltage across the resistor, and we have a battery supplying a positive 1.5 volts, where's the voltage drop? Well, again, assuming our usual assumptions about wires not having any resistance of that was worth the name, that implies that the voltage across the inductor, or the maximum amount, if we will equal the same thing as the battery which is 1.5 volts. And that will happen at time equals 0, the moment that we throw the switch. Okay, that's kind of an interesting concept. Now, as time goes by, current starts to flow through the circuit, we'll see changes, right? That's sort of the point. But it's kind of an interesting statement to make, that at the beginning of the process is when you have the maximum voltage across the inductor. Now, by the same token, the maximum voltage across the resistor will also equal the battery's voltage, which is that. What does that mean? When we have current at its maximum, when current is flowing through the entire circuit, that will mean that there's no voltage drop across the inductor. Now, again, this will be something that you can talk about with your instructors or refer to other videos. I'll simply say here that the voltage drop across an inductor depends upon the change of current specifically, very emphatically. If the current is a maximum, by definition, it's no longer changing. There's no change of current. There's no voltage drop across the inductor. Strangely enough, you don't have one. And that means all the voltage drop is across the resistor. So after an indefinite amount of time, we've waited long enough for everything to do what it's going to do, all the voltage will be at the resistor voltage drop. So at time going off indefinitely into the future, which we can symbolize as going off to infinity. We've also had that discussion about how in the terms of the equations, you would have to wait an indefinite or infinite amount of time for the current to reach a maximum, for the voltage across the resistor to reach a maximum, so on and so forth. We've also talked in practical terms that if you wait 5 or more time constants, you're pretty much done. So we're not going to belabor that point here, just simply state it. All right, so there are no calculations here, but there's a worthwhile discussion as to when these occur. All right, what about the maximum current through the circuit? Well, the maximum current through the circuit will happen if we wait long enough, but equation-wise, it's the same calculation as you've had before. So maximum current is simply the voltage divided by resistance. So 1.5 volts, we have 20 ohms, like that. So 1.5 divided by 20 is 0.075 amps, or if you prefer, 75 milliamps. Right? We'll stick with the 0.075. We'll stay with our standard units as we usually do. Okay. So that's an interesting statement, though, to make, is that the maximum current doesn't happen until towards the end, if you will. In fact, at the end of the process, not the beginning. Okay. What is the time constant of a circuit like this? Now, a time constant for a RC circuit was RC. It was a very simple thing to say. But the time constant for an RL circuit, and by the way, if you look online or in notes, you might also see it as LR. Doesn't really matter the order of the letters. It's L divided by R, the inductance divided by the resistance. And what is that? That's 4 times 10 to the minus third henries, 4 millihenries, but written in standard, right? And 20 ohms, like that. Okay, so that means 4 divided by 20 is 0.5, if you will, 0.05 times 10 to the minus third. So if we do this carefully, excuse me, I'm sorry, not 0.5, 2, sorry, got my numbers mixed up. Be 2 times 10 to the negative 4th seconds. It's one of those deals, I had it written in my notes correctly and I didn't say it correctly, but this is correct. And if you prefer 0.2 milliseconds, if you want to write it that way, but again, let's stick with this number here if we need to use it. Okay. Notice that the time constant is very short for realistic numbers in a circuit. So our L circuits, as a general rule, tend to have very quick time constants. Not a big deal, but something that's worth talking about. All right, so what about the behaviors of the voltage and the current flowing through the circuit? So I've already stated this, but let's do some plots first to kind of illustrate how this might work. So in this particular case, let's talk about the current first. There's your maximum current. And we'll plot current versus time like this. In the case of an RC circuit, the current started at a maximum value and went down exponentially. We are going to start at 0 and increase exponentially. and it's going to look like this. That's the general sense. This line here is going to eventually keep on approaching this maximum value until all said and done. This will also be the same picture for the voltage across the resistor. Will have the same appearance. On the other hand, if we were to talk about the voltage across the inductor, which is VL, and here's your maximum value, so again, Vmax if you will. As we talked about before, the maximum voltage across the inductor is at time 0, and then it'll be an exponential drop. And it looks something like this. Okay. The formulas would be something along these lines. So current as a function of time is our maximum current, and then 1 minus e to the negative t over tau, like that. The voltage across the resistor has the same sort of approach because it also is increasing as time goes by, but the voltage across the inductor is decreasing from a maximum value and looks like this instead. Now, we've already talked about this in a previous video, that one-time constant, you will e to the minus 1, if you will, is 0.368, round it off a little bit. Or, if you would like to say this, if you talk about the voltage across the inductor, it starts at a maximum, it's down to about 37% of its original value. If, on the other hand, you talk about the current through the coils or the rest of the circuit, or the voltage across the resistor, that's 1 minus 0.368, or roughly 63% of its value going up. Again, we've talked about this in a previous video. So I'll let you go ahead and do your calculations on your own to show what the specific numbers would look like, but these are the formulas that you would use to make those calculations. Long story short, an inductor is a magnetic device. It stores magnetic energy. It operates using current, whereas a capacitor is really an electric device. It stores charge. And so they have kind of opposite behaviors for that reason. So the current, say, when you throw the switch on a RC circuit, will behave with an actual exponential drop, kind of like that. But the current for an RL circuit starts at 0 and increases this way. And so on and so forth. So a lot of things are sort of opposite. But the math is very similar, right? The one other exception to the math, the time constant for an RC circuit was RC, but the time constant formula for an RL circuit is L divided by R. And again, if you want to check on the units, you can see how that works. All right, our technical support is given to us by Sidney Gautrow and Sophia Turner. Funding for this program comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla, broadcasting from Hattiesburg, Mississippi. Thanking everybody for your attention, as always, and clear skies.